right, let's do this starter. We have an ice cube. Shh, quiet please, look up here. We've got an ice cube. It has a mass of 15 grams and is at the melting point temperature, which is 0 degrees Celsius. You throw the ice cube into a lake at 10 degrees Celsius. That is, the lake is 10 degrees Celsius. How much heat flows into the ice cube as it melts? Or after it's melted, when it's all done melting, how much heat did it absorb? And then what is the change in entropy for the ice cube? And then what is the change in entropy for the lake? And with this caveat, its temperature does not change. That is, the ice cube did not absorb enough heat from a huge body of water to change its temperature by any measurable amount. So what is the overall change in entropy for this process? Question mark. Okay. So let's solve it. Okay, so given. So we have a little ice cube here. Now sometimes I put, so the mass of this is, I'm just going to go ahead and change it to kilograms. Now it's at 0 degrees Celsius, so what's its temperature? 273 Kelvin. Yeah, we'll just say it's at 273 kelvins. Is it okay to do unit conversions like that in given? Yeah, you can. Just makes it a little. Now here's the Lake Superior. Mm-hmm. Little self-portrait. Anyway, it has a temperature of, well, it's 10 degrees warmer than that, so what would that be? 283 kelvins. So what do we want to find? So this is going to go, whoop, we're going to throw that into the lake. And we want to know, let's see, for part A, what's the heat? What is the change? How much heat flows into the ice? So this is the heat for the ice. And then B, what is the change in entropy for the ice? And then C, what is the change in entropy for the lake? And delta S is what we use for change in entropy. I don't know why they use S, but they do. And then D, what is the total entropy change? And then we get that, we're just going to add those together. So let's solve it. Q equals, it has to absorb this heat, so heat's flowing into it, it's going to be positive. And it's going to be the mass times the heat of fusion for ice. So this is 0.015 kilograms. And what is the heat of fusion? 3 point something?
3.34 times 10 to the 5th.
And what are the units? Joules per kilogram. So if you had 1 kilogram of ice, it would take this much energy to melt that much ice. If you have one liter of ice, that's how much energy it's going to be absorbed. All right, so, this is all for part A. So Q is equal to 0.015 times that. Did you get 5,010?
Yeah.
Always box your answers, please. All right, part B. Now, delta S for the ice is equal to Q over T. And so this is 5,010 joules. And the temperature of the ice was, what was it? 273 kelvins. So take that, divide by 273, and 18.35 joules, or 18.4 Kelvin, joules per Kelvin. Did you get that? Now, the tricky one is part C. For the water, and I'm sorry, I'll zoom in. Now for the water, what happened? It lost heat. So that's a negative. But it lost the same amount of heat that the water gained. So if the water gained 5,000 joules, that came at the expense of the water losing that energy. And we said its temperature is 283. And when we do that, I get 17.7. Negative. So what was our overall, what's our total change in entropy? We just add these together. So, so 18.35 minus 17.7 equals, you have 0.65? Joules per Kelvin. So the entropy of the universe increased by that much. Now, this is not a unit that makes a lot of intuitive sense. I mean, what does that mean? I don't even really have a good feel for it. Except that it does mean that this quantity pretty much it always increases. You have any closed process that happens where heat leaves a high temperature and flows into a low temperature, this has to always be positive. Overall change. So like the water, we extracted heat from it, so its entropy decreased. But the increase in entropy for the ice was greater than the decrease for the water, so overall we had an increase. Any questions?
That is all.
That is
all.